In astronomy, when we look up at the sky and see stars and planets and other objects, we notice that some objects are brighter than others. Magnitude is a quantitative way that we could compare the brightness of different objects. When we think about magnitude, there are two ways we could consider this concept. We could think about the notion of apparent magnitude, which talks about how bright an object appears to be, or we could consider the notion of absolute magnitude, which talks about how bright an object really is. To think about apparent and absolute magnitude, imagine you have a small candle and a giant bonfire. Now, if the small candle is very close to you and the giant bonfire is very far away, way off in the distance, the small candle could appear to be brighter to you than the giant bonfire. You know from everyday experience that the giant bonfire really does give off more light, but the fact that the giant bonfire is just so far away from you, the small candle appears to be brighter. This is a statement considering the notion of apparent magnitude. Absolute magnitude talks about how bright an object intrinsically is. So if you imagine that we take whatever objects we are considering, like a candle and a bonfire, we place them at the same distance away. Now we're kind of comparing the brightness on equal footing, and because the giant bonfire gives off more light than the candle, the giant bonfire would appear brighter if they are at the same distance. When we compare them on equal footing, now we would say the giant bonfire has a greater absolute magnitude. For this course, we're really only going to talk about apparent magnitude for the sections that we're covering, and I'm just going to quickly point out the difference in these quantities, the symbol m sub v and m sub v. This is a lowercase m, and this for absolute magnitude is an uppercase m. And the subscript v, I think, just means we're talking about visual light, because if you think about brightness as the amount of light given off, well, you could talk about light given off in the visual part of the spectrum, or you could talk about light given off in infrared colors or in X-ray colors or in radio colors. The subscript V just means we're talking about visual light. The magnitude scale is often attributed to the Greek astronomer Hipparchus, possibly formed somewhere in the range 190 to 120 BCE. The first time the magnitude scale appeared in writings, as far as we know, was in the writings of the astronomer Ptolemy around the year 140 AD. So originally, stars were divided into 6 magnitudes of brightness. The brightest stars were assigned first magnitude, the dimmest stars were assigned 6th magnitude. And these stars were just barely at the limit of what humans with good eyesight could see. Now, this magnitude scale is in a way inverted. A brighter object will have a smaller magnitude, a dimmer object will have a larger magnitude. So it's kind of like golf, where the lower number is brighter in a way of thinking. In ancient times, due to a lack of precise measuring equipment, due to a lack of technology, magnitude pretty much had to be guesstimated. But today, because we have technology that could photograph objects, collect light from distant objects, and be very precise in how it measures things, magnitude can be measured to a relatively high degree of precision. And due to our ability to precisely measure the brightness of objects, magnitude does not need to be whole numbers anymore. In other words, magnitudes could take on decimal values like 4.3 or 5.927. Also, the brightest objects in the sky can have, if we follow that higher numbers mean dimmer magnitude, the brightest objects can go into negative magnitudes. The sun has an apparent magnitude of around negative 27 because it is incredibly bright. Meanwhile, the Hubble Space Telescope can see objects as dim as magnitude 28. So, if we're going to talk about magnitude, magnitude is related to the notion of flux. And flux is not the same as the brightness of an object, but flux is related to the brightness of an object. So before we're actually going to define formally what is flux. Let's imagine that we have a telescope and we have that telescope aimed at some object in the sky. And I want to ask you, what factors will affect the total amount of light that enters that telescope? So here we have some light from a distant object entering our telescope. Well, it seems to reason that the amount of light that enters the telescope will depend on the inherent brightness of the object. So if I'm looking at a star in the sky, is that star inherently very bright or inherently kind of dim? That will affect how much light enters the telescope. Also, how far away is that object? If the object is kind of close to us, then it will have a lot more of its light enter our telescope compared to if that object is really, really far away. Also, the size of our telescope will affect the amount of light that enters the telescope. If I have a telescope that is 2 inches across, I could collect so many particles of light per second. But if I have a telescope that is 300 feet across, I could collect a lot more light with my telescope, just because my telescope is so ginormous. Formally, flux could be defined as the amount of energy hitting a surface per unit time per unit area. So basically, when we define flux, we are just asking how much light will hit each square inch of my telescope every second. So if I want to think about flux will depend on the inherent brightness of the object and the distance to the object, because that will affect how much light is approaching my telescope every second. But flux will not depend on the size of my telescope, because flux is asking how much light hits each square inch of my telescope. It isn't asking how much total light will hit the telescope itself. Now, flux is going to be related to the brightness of an object. So let's consider two stars of different brightness. We could use Castor and Pollux from the constellation Gemini. We said earlier that Pollux is 40% times brighter than Castor. So that would mean that 40% more light will enter my eye, or 40% more light will enter my telescope when it's looking at Pollux compared to when it's looking at Castor. So that implies that Pollux will have a lower magnitude than Castor, because remember, a lower magnitude means a brighter object. Magnitude itself is formally defined so that if object A is 100 times brighter than object B, the brightness of object A will be 5 orders of magnitude less than the brightness of object B. So, before I discuss magnitudes more, I want to take a moment and, as an aside, think about what it means to double a quantity. So let's pretend we have some quantity. If that quantity grows as 2, 4, 6, 8, 10, 12, and so on, this quantity is not doubling. A quantity that grows like 2, 4, 8, 16, 32, 64, on and on, this is what is doubling. In the first case, we are only adding 2 each step along the way. We're not doubling. In the second case, we are multiplying by 2 each step along the way. We are doubling. And this second way of increasing a quantity is how we kind of want to think about magnitude. Now, the astronomical magnitude scale behaves just like doubling a quantity, but instead of doubling, which is the same thing as multiplying by 2, we're going to multiply by 2.51 each step along the way. Now, this number 2.51 does seem odd, but I'm going to show you in a moment where it comes from, why it is. So, if I say 2 times 2 times 2 times 2 times 2 is 32, doubling a quantity 5 times gives me something 32 times larger than the original. If I say 2.51 times 2.51 times 2.51 times 2.51 times 2.51, well, if I increase some quantity 2.51 times, and I do that 5 times, I get 99.63. So after 5 steps, I increase that quantity by almost 100 times, which is how we're defining the difference in magnitude. Now, let's suppose we have a 6 magnitude star that has an apparent brightness of 20. I did not define what I am using to measure brightness. The actual units of how brightness is measured is not important here. Let's just pretend a 6 magnitude star has 20 units of brightness. Well, a 5th magnitude star will be 20 times 2.51. So a 5th magnitude star will have 50.2 units of brightness. A 4th magnitude star will be 2.51 times brighter than a 5th magnitude star. So a 6th magnitude star has 20 units of brightness. A 5th magnitude star has 50.2 units of brightness. A 4th magnitude star has 126 units of brightness. A 3rd magnitude star will be 2.51 times brighter than a 4th magnitude star. So a 3rd magnitude star will have 316 units of brightness. A 2nd magnitude star will have 794 units of brightness. I'm just rounding up. And a 1st magnitude star will have 1992 units of brightness. So each jump along the way from 6 to 5, 5 to 4, 4 to 3, on and on, I increase the brightness by 2.51. And after 5 jumps, after 5 orders of magnitude, I have an object that is pretty close to 2,000 times brighter than the original. 1992, I'm going to round up to say 2,000. So I could say a 1st magnitude star has 2,000 units of brightness. A 6th magnitude star has 20 units of brightness. The 1st magnitude star is 100 times brighter than the 6th magnitude star. Now, I told you this number 2.51 looks really weird. The actual number in increase in brightness is not 2.51. There are more decimals after this. So in actuality, each drop in magnitude or each change in magnitude increases the brightness by 2.5111886432, blah, blah, blah. There are many more numbers that we would have in this decimal. But we just round to 2.51. If we were to keep the actual number, this number would be 2,000 and we won't need to round anymore. And I could find that mathematically. If I say this number is equal to raised to the 5th power is equal to 100, because I multiply 2.511, blah, 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 all the decimals by itself 5 times. I found that by taking the 5th root of 100. So don't worry about this equation per se. You won't really need to use this 2.51 to the 5th or the 5th root of 100. I just want to show you where this comes from. So how could I write the difference between a 3rd and a 5th magnitude star? Well, I see the number 3 and I see the number 5. So I know that these 2 stars are going to be 2 magnitudes different from each other. So if I look back here, the 4th magnitude star would be 2.51 times brighter than the 5th magnitude star. The 3rd magnitude star will be 2.51 times brighter than the 4th magnitude star. So that's 2 jumps in magnitude. So I could write this as 2.51 times 2.51, or more formally 2.51 raised to the 5 minus 3. And so this would be 2.51 squared and 6.3. So I could say the 3rd magnitude star is going to be 6.3 times brighter than the 5th magnitude star. Now, why did I have a 3rd magnitude and a 5th magnitude star? I know those 2 stars are 2 magnitudes apart, 3 to 4 to 5, that's 2 orders of magnitude. Why didn't I just start right here, 2.51 squared? Well, if I think of it in this way, 2.51 raised to the dimmer magnitude minus the brighter magnitude, I could extrapolate this to any magnitude. And with improvements in precision of measurements, stars don't need to have magnitudes that are necessarily whole numbers. And the magnitude scale could also be extended to allow for very bright objects with negative magnitudes. So if I look at the brightest star in the sky other than the sun, Sirius has a magnitude of negative 1.46. Vega, the brightest star in the northern hemisphere sky, has a magnitude barely above 0. Castor and Pollux. Castor has a magnitude of 1.51. Pollux has a magnitude of 1.14. So I could plug in any star here to be the dimmer one, any star here to be the brighter one, and find out how many times brighter the brighter star is compared to the dimmer one. And so I don't necessarily need to only consider a fifth and a third magnitude star. For example, if I want to compare the brightness of Castor and Pollux, I could say, okay, 2.51 raised to the dimmer star minus the brighter star, so that'd be 1.51 minus 1.14. I could say that's 2.51, 1.51 minus 1.14. I put that in calculator, I get 0.37. When I actually then put that in a calculator, because I would not bother solving this by hand, I get 1.14. So I could say that Pollux is 1.14 times brighter than Castor, or about 40% greater than the brightness of Castor. In general, the difference in apparent brightness, which could be written as the difference in flux between star A and star B with magnitudes MA and MB, could be written like this. So the flux of star A divided by the flux of star B is 2.51 raised to the power of the difference in magnitudes. So that's 2.51 raised to the power of, and remember that lower magnitudes mean brighter objects. If star A is brighter than star B, then I expect the flux from star A to be bigger than the flux from star B. And if the flux from star A is bigger than the flux from star B, this fraction on the left-hand side will be some number bigger than 1. On the other hand, if star A is dimmer than star B, well, that means FA is going to be smaller than FB. And if FA is less than FB, then FA divided by FB is going to be some number less than 1. Also, notice the positions of A and B in this equation over here. Here, A is upstairs and B is downstairs, but on the right-hand side, I have MB minus MA. So in a way, the way my mind looks at it, on the left side, A comes first, B comes second, but on the right side, B comes first and A comes second. I just wanted to take a moment to point that out, just so you accidentally don't flip it and get one side having the wrong order of star A and star B. Now, this equation above allows us to calculate the ratio of fluxes, or compare the brightnesses of the magnitude of two different objects. And after this video, I'm going to have an example problem where I work through something using a problem like this. It is possible to mathematically invert this equation, and this will allow us to calculate the magnitude of brightness of objects when we are given the fluxes, or the ratio of fluxes of two objects. And when I do that, I'm going to demonstrate how you get from this equation up here to this equation down here in the next video. I could say the difference in magnitudes of A and B is 2.5 times the log of FA divided by FB. Now, very often you will not be given the fluxes themselves. You won't say star A has a flux of 4 and star B has a flux of 3. You'll be given the ratio of the fluxes, or this star is this many times brighter than that star. For example, if you are given star A is 4.3 times brighter than star B, I would say, okay, FA over FB is going to be 4.3. Now, if you think about it, it doesn't matter if FA is 4.3 and FB is 1, or FA is 17.2 and FB is 4. In the first case, 4.3 divided by 1, that gives me 4.3. In the second case, 17.2 divided by 4, that also gives me 4.3. So it doesn't matter how you write it. Very often you'll just see star A is this many times brighter than star B, and you know that is just FA divided by FB. In both of these cases, as I said, FA is 4.3 times greater than FB. So to summarize what we're talking about, if you are given the ratio of the fluxes and you're asked to find a magnitude, use this equation. So here we're given the ratio of the fluxes. This is sometimes phrased as star A is this many times brighter than star B. Magnitude is already isolated by itself. It's just downstairs all by itself. So this is what you want to find when you're looking for magnitude. If you're asked to find the ratio of the fluxes, very often this is phrased as how much brighter is star A than star B. Then you would use this equation where FA and FB are already by themselves and the magnitudes are up here in the exponent of this equation.